The last term in the energy balance that we'll discuss is heat. In engineering, when we discuss heat, we are usually referring to heat transfer or heat flow. So in engineering, heat typically refers to heat transfer or heat flow. Right. And this heat transfer or the heat flow, in contrast to work, heat describes energy transfer, energy interactions that are thermally driven. Or in other words, system and surrounding interactions and the energy transfer between the two, so energy interactions, due to a temperature difference. Okay? Now when we talk about heat, this is all going to be occurring at the microscopic scale. So these energy interactions. So it occurs at the microscopic scale. And in some sense, the way you could think about it is that heat is just microscopic work. And we'll go over, the reasons for saying that in a bit. In any case, when we talk about heat in this course, the sign and the magnitude of Q are going to depend on what the system boundaries are. So to illustrate this concept, we'll go to one of my favorite examples, which is dealing with cooking a pizza. All right? And so if you're using an oven to cook your pizza, basically the setup that you have is you have some sort of tray or grill that your pizza sits on. And then in the back of the oven, there's some sort of heating coil that gets hot and then, transfers heat from the coil to the air in the oven and then eventually to your pizza. So this is heater. Okay? And let's say that when you initially put the pizza into the oven, it is at around room temperature. But when you put it into the oven, you had already preheated your oven to 400 degrees Fahrenheit. Okay, so these are all typical values. Now when we talk about heat transfer in this sort of situation, the heat transfer, or the value of Q and the sign of Q, are going to depend on what we define our system to be. And so if we define our system to be the pizza, heat is going to go into the system from the hot air in the oven. So if pizza is the system, then your Q value is greater than 0. On the other hand, if we set the system to be the entire oven itself, and assuming that your oven is good enough, it's going to be somewhat well insulated and it won't let too much hot air out of the oven. Okay? And so if that is the case, if the oven is a system, then we could approximate Q as being 0. Or in other words, we could say that this system is well insulated and that it's adiabatic. Okay? And so those are the sort of general bird's eye view of what heat is. But now let's kind of think of it more from a first law perspective. Okay? And so what we're going to consider now is heat transfer between two systems that are connected by a diathermal wall. heat between two systems separated by a diathermal wall. And by diathermal wall, all that means is that the heat transfer between the two compartments is going to be instantaneous or infinitely fast. Okay? And so for our system, let's just think we have one big rectangle that's split in half. The left side is compartment A, and the right side is compartment B. Okay? And let's say that there's heat transfer between the two sides, so that QA is going to go from compartment A to compartment B, and QB is going to go from compartment B to compartment A. Now from our energy balance, if we simplified it out, we would see that the change in energy in compartment A is due to heat leaving compartment A. Okay? And the change in energy of compartment B is going to be due to the heat that's leaving compartment B. And if we can try to look at the change of energy of the entire system, right? So I'll call this delta E of, just a total delta E. That would be equal to the sum of delta EA plus delta EB. And we would know that because there's no heat leaving out of the entire system, that its change of energy would just be equal to 0 if we added those two changes of energies up. On the right-hand side of the equation, we would be adding up our two heats. And so from here, we see that the sum of our two heats has to equal 0. Therefore, the heat leaving from compartment A to compartment B has to be equal to the negative of QB. Okay? All right, and so that's the, just from a simple energy balance analysis. The other thing I want to say is that if the change in energy of compartment A is negative, conversely, that would have to mean that the change in energy of compartment B would have to be positive. And when we have this sort of situation, what we observe is that energy transfers from A to B in the form of heat. Okay, so that's what we observe. But that brings up the question, why do we observe it in that order? Right? Why do we observe energy transferring from compartment A to compartment B rather than the reverse? Right? We never see the reverse situation occur. And so to get a better idea of why the energy is transferring from compartment A to compartment B, we could just start to think about the system at the microscopic scale. So let's examine the system at a microscopic scale. Okay. All right, and so let's examine the system at the microscopic scale. And so what I'm drawing here is that wall that separates compartment A from compartment B. On the left-hand side here, we have compartment A, and on the right-hand side, we have compartment B. All right? And so, on the left-hand side, is our system, and let's say it's filled with some sort of gas. This gas is made up of molecules that are once again moving around. Right? Imagine it's the same sort of gas we used when we were talking about the force balance. Okay? And so these molecules are moving around, and their speed, is dictated by how much energy they have. And so if side A was at a higher temperature, that means these molecules were moving around very quickly. Right? They're moving around all over the place. Well, when they're moving around, these molecules can also accidentally collide into the wall. Okay? And when they collide into the wall, in contrast to the assumption made before when we said it was an elastic collision, what we could say is that when they hit the wall, the molecules will transfer some energy from themselves to the molecules in the wall. Okay? And when that happens, after the molecules recoil, what they do is they end up slowing down. Okay? Alright, the molecules slow down, and they transfer some of their energy from themselves to the molecules that make up the wall. And so if we draw out the molecules that make up the wall, we could draw them kind of like this. Let's say they're bonded together. That's what the little spring-looking thing is. And so when the energy is transferred from the hot gas molecules on side A, their energy is transferred to the molecules on the wall, and that causes the molecules in the wall to vibrate faster. Right? And the energy transfer starts on this end of the wall, and it's slowly transferred to the right side of the wall. This part starts vibrating faster than the right-hand side of the part, but eventually the entire molecule will start vibrating at that same speed. And so what's happening here is the energy is being transferred through the wall. On the right-hand side of the system, we also have molecules that are floating around. And because side B was at a lower temperature, this means these molecules were moving around much slower than the molecules on side A. But once again, these molecules can also run into the wall as well. And so when they run into the wall, basically what happens is the energy that was being transferred from side A transfers through the wall, and then it's transferred to any molecules that are touching the wall on side B. And so what happens is any molecules on side B that are touching the wall as that energy is being transferred, what happens to them is they end up getting faster. They end up moving faster. Okay? And so just to explain in words, what's happening at the microscopic level, if system A is initially hotter than B, then the A molecules are moving faster than B. Okay? And when the A molecules hit the wall, they end up transferring their momentum, or essentially their microscopic kinetic energy, through the wall to side B. Okay? And so in the end, this doesn't just happen with one or two molecules. It happens with 10 to the 23 molecules. A lot of molecules, Avogadro's numbers of molecules. And so a lot of these collisions are happening. And so the net result of these many collisions is basically just heat transfer. Right? The end result of all those collisions is that side A gets colder because the molecules slow down, and side B gets hotter because the molecules start to heat up. Okay? And so in general, when you think of heat transfer, at least from a molecular perspective, heat transfer is just going to be due to random microscopic work done by molecules of one system on another. All right, and so that's, you could think of heat as microscopic work, and then as regular work as a macroscopic work. Okay? And so in this course, we're going to focus on connecting the sort of molecular perspective to what we observe with our own eyes.